Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course.
Alright, question number 2. Here we're given a problem that's very similar to the one that we just completed, and so we'll be able to go through this rather quickly. So looking at the mass spec data first, we see M over Z of 108 being our molecular weight of the compound, so that's our 100% relative abundance. So this is the molecular mass, 108. The 109, this is our M plus 1 peak. We can take that 7.82% divided by 1.1% to get an approximation for the number of carbon atoms. In this case here we get 7.1, and so we know that there are 7 or 8 carbons in this compound. And then looking at our M plus 2 peak, we see that this value is less than 4%, and so there should be no sulfur, chlorine, or bromine. So let's go ahead and start out by assuming that we have 7 carbon atoms, and so 7 times 12 gives us 84, and then 108 minus 84 gives us 24. So we have 24 atomic mass units to dish out to hydrogens, oxygens, and possible nitrogens. If we had 0 nitrogens and 0 oxygens, then we would have a molecular formula of C7H24. Now this violates the hydrogen rule. There's no way that we could have this many hydrogens with only other carbon atoms, and so this can't be right. Suppose instead that we had 1 oxygen atom. So that would take away 16 AMUs from this 24, leaving us with a possible molecular formula of C7H8O. Now this is an acceptable molecular formula that we can potentially use. If instead we guess that there were 8 carbon atoms, then we would have 108 minus 96, leaving us with 12 AMU, which is too few to include another oxygen or nitrogen, meaning that the molecular formula would have to be C8H12. However, we can go ahead and reject this because it does not fit the HNMR integrals. Nor does it have an oxygen, which is probably what is causing this broad peak here in the IR spectrum, so we can go ahead and eliminate that. We can then calculate the degrees of unsaturation of this compound using the equation that I provided under solving problem 1. And so you can calculate that out to be 4, which means that we have either 4 rings and or pi bonds and a possible benzene ring again. Now let's look at the IR. As I just mentioned, we do have an OH stretch present, so this is that very broad peak that we see here. That's centered around 3320 wave numbers. In this region, we don't see any peaks that could be attributed to amine or amide bonds or NH stretching. And then we shouldn't anyway because we don't expect to see a nitrogen in our molecular formula. There's no peak around 2200 wave numbers or so, and so likely there's no terminal alkyne present in this compound. Likewise, not enough degrees of unsaturation to account for that, as well as a benzene ring, which we probably have based on our overtones here and our peaks around 1500, 1600 due to the stretching for that benzene ring. We do have, just like in the previous problem, some bands that could be attributed to aryl or the vinyl CH stretching present just greater than 3000 wave numbers, as well as some present just shy or just lower than 3000 wave numbers. Also, we don't see the very strong band attributed to a C double bond O or carbonyl stretch, and so we don't have enough oxygens for that anyway, and so we can go ahead and assume that we have an alcohol. So again, we very likely have a benzene ring just like the previous problem, and also probably an OH group. So let's look at the HNMR data now. So just like in the previous problem, we have this multiplet of integral 5 in the same chemical shift region as before, and so likely this is attributed to the phenyl group, C6H5, the hydrogens for that group. We have a singlet at a chemical shift of 4.51 with integral 2, so we have 2 hydrogens here. This is likely due to the hydrogens attached to a carbon, like so. And then with a chemical shift of 3.18 ppm, a singlet with integral 1, and so we have 1 hydrogen. This is very likely attributed to the hydrogen that's attached to the oxygen in our alcohol. And so what this generally means then, because we can't have the alcohol group directly bound to a benzene ring, we have this CH2 group separating them, meaning that this is the only possible structure that we can have here.